A skier weighing 50 kilograms pushes off the top of a ski slope with a force of 85 newtons directed down the slope. The push lasts 1 second. The slope is inclined at 30 degrees and is frictionless. What is the initial acceleration of the skier during the push-off? So, to figure that out, let's start by drawing a free body diagram. So, let's say that this is the slope. This is the angle, theta, which we know is 30 degrees, but I'm just going to write theta for now. Here is the skier. So, since it's on an incline, you have the force of gravity acting perpendicular, or not perpendicular, the force of gravity acting straight down. The normal force is acting perpendicular to the incline. And here you have the component of gravity parallel to the incline, which is mg sine theta, and the component perpendicular to the incline, which is mg cosine theta, because this forms a right triangle and the angle theta is the one over here. You can prove using some geometry corresponding angles and stuff. And along with this force of gravity, I'm going to draw another arrow up here, but just know this is supposed to be coming out from this dot as well. I just don't have enough space here. And this is the force of the skier's, let's say, push. He pushes off the top of the ski slope, and the force is directed down the slope. And so it's also pointing in the same direction as mg sine theta, or the force of gravity parallel to the slope. And note that for this problem, we're going to say that the positive x direction is actually pointing down the slope, since that is going to be a lot more convenient to use. So from Newton's second law, we know that the net force, or the summation of all of the forces, is equal to the mass times acceleration. So let's find the acceleration in the x direction, and that is the initial acceleration of the skier. So in the x direction, we have the force of the push as well as the force of gravity, or mg sine theta. And that is equal to the mass times the acceleration. And I'm going to put a little p subscript because this is during the push. So now we just need to solve for the a. So the acceleration during the push is equal to the force of the push divided by the skier's mass plus g sine theta. We just divide both sides by m, and these two cancel out. So this becomes the force of the push is 85 newtons divided by the skier's mass of 50 kilograms plus gravitational acceleration 9.8 times sine of theta, where theta is 30 degrees. So now this simplifies to, if you plug this into a calculator, this should give you 6.6 meters per second square. And that is the initial acceleration during the push. So I'm going to rewrite it up here. So the initial acceleration during the push-off is 6.6 meters per second squared. After the push-off, the skier continues to travel down the incline for another 2 seconds. What is the total displacement of the skier during the first 3 seconds? So we can break this problem down into 2 parts. For the first stage, let's say this is a skier, you have the force of the push as well as the force of gravity, mg sine theta, parallel to the slope that's propelling him down. In the second stage, this is a bad incline, but it illustrates it, okay? You have only the gravity component, mg sine theta. Since in the second stage, the skier has stopped pushing. He has finished his push-off. So the acceleration in the first section is going to be greater than the acceleration in the second section due to the additional force from the push of the skier. So we're going to break this down into 2 stages. So first we need to calculate the distance traveled during the first step. And there's this kinematic equation that says that the displacement is equal to the initial velocity times the time interval plus 1/2 times the acceleration times the time interval squared. So for the first part, we're changing x1. The skier has no initial velocity, so we're going to assume that he has no initial velocity since he pushes himself off the top of a ski slope. So its initial velocity is 0 meters per second, so we can ignore this part. So it's simply equal to 1/2 times the acceleration. In this case, the acceleration is the acceleration of when he is pushing times the time interval squared. And this is equal to 1/2 times 6.6 meters per second squared times the time interval of 1 second squared. And this just gives you 3.3 meters. So changing x1, or his displacement during the first part, where he's pushing off the slope, is going to be 3.3 meters. Now we need to find the second part. So notice that after this push-off, he has already accelerated. So even after the push-off, if he isn't still applying a force from the push, he still has the initial velocity from that greater acceleration of the push. So we can figure out his velocity after this first second by using another kinematic equation, which says that final velocity is equal to the initial velocity plus the acceleration times time. Again, the initial velocity is 0 since he starts by pushing himself off, so we can ignore that. So the final velocity is simply equal to the acceleration times the time. So this is simply equal to 6.6 meters per second squared times the time of 1 second, which gives you a velocity of 6.6 meters per second. 6.6 meters per second. And so this is his velocity at the end of 1 second. So after 1 second of traveling, he has a velocity of 6.6 meters per second. Now for the next 2 seconds, he is not pushing against the incline. So the net force will simply just be mg sine theta, since that's the only force acting on him in the x direction while he's skiing down. So that must equal his mass times his new acceleration, which I'm just going to call A for now. I'm just not going to write any subscript since I already wrote a subscript for the initial acceleration. So again, we solve for A. A is equal to g sine theta, since the masses both cancel each other out. So the acceleration is equal to 9.8 times the sine of 30. 9.8 sine 30. And sine 30 is simply equal to 1/2, so it's 9.8 times 1/2, which is equal to 4.9 meters per second squared. So the acceleration during the second part here is equal to 4.9 meters per second squared. So I'm going to write that. So acceleration for the second part is equal to 4.9 meters per second squared. So now to find our next change in displacement during the second stage, we simply use this same equation again, except this time we have an initial velocity, which is actually this final velocity here that we calculated. And again, the initial velocity of the second stage is when the first stage stops, and this velocity is the velocity of the skier after the 1 second, or the first stage. So the initial velocity when beginning the second part, where he stops pushing, is 6.6 meters per second. And then he continues for another 2 seconds. And in this problem, it only asks us for the total displacement during the first 3 seconds. So for the next 2 seconds, we have 2 more seconds remaining. Then we're going to add 1/2 times the acceleration, which we calculated to be 4.9 meters per second squared after he stops pushing. And we're going to multiply by the time interval squared, which is 2 squared. Now, simplifying all this, you should get that the displacement during the second stage is actually 23 meters, which is quite a lot more distance compared to the first stage where he was starting to accelerate. So now we have both of our displacements necessary to figure out the total displacement. Found that the displacement during the first second is equal to 3.3 meters, and the displacement during the second, the latter 2 seconds, or the displacement during the second part, is equal to 23 meters. So the total displacement is simply the displacement from the first second plus the displacement from the second and third seconds. So it's the displacement from the first stage when he is pushing plus the 2 seconds after where he lets gravity take over to accelerate him. And we've already calculated these values here. So this is simply equal to 3.3 plus 23. So I forgot the x here. So the total displacement after 3 seconds is going to be equal to 26.3 meters. And that is how you would solve this problem here.